In this video, we will explore the different primitive data types supported by Java. But first, what is a data type? Let's take an example to understand. This is an example of an OOP-based solution to calculate the hourly pay of an employee by knowing his gross pay and hours worked. Assuming that the work allows increments of an hour with no fractions. In this case, we can consider the hours variable as an integer. That is, whole number without fractions like 8 or 10. Now, what about the other attributes? Pay or rate, both of these could be fractions. In this case, we cannot refer to them as integers. They must be of a different data type other than an integer, a data type that allows for fractions. This is what we mean by data types, and what we want to learn is what other data types does Java support. Before we do that, let's see how data are stored in a computer memory. By now you probably know that data in computers are stored in a bit. The bit is a computer data unit that can store one of two numbers, 0 or 1. We only have two numbers in computer because these are the two signals that we can distinguish using electronic signals, 0 volt or high volt. This is very limiting, so if you want to store more numbers, add more bits. For example, if we add 2 bits, we can now represent 4 numbers corresponding to the 4 possible combinations, 0, 0, 0, 1, 1, 0, and 1, 1. So you got the idea. Add more bits, represent more numbers. When you have 8 bits together, this is referred to as a byte. In a computer memory, slices of bytes are stacked together to form what is called a stack memory. This is the RAM you buy for your computer. So when you say I bought 32 gigabyte RAM, you actually say that you have 33.5 million slice or byte. So what happens in the memory when you type in Java compiler something like int hours equals 10 semicolon? What happens is that Java will go to the memory, reserve 4 bytes, call them hours, and write the value 10 in them. But why 4 bytes? That's exactly why we need to learn about the different data types. Java supports 8 primitive data types. The reason we call them primitive is that they are there and are not derived from classes. Also, you don't need to build a class to use them. What that means for us is that they are not objects and they don't have attributes or methods. And that's why they are referred to as primitive data types. Each data type is treated differently, meaning each data type is allocated a specific amount of memory slices or bytes. It also dictates what a variable with a specific primitive data type is capable of doing and storing. That's why it's very important to select the proper data type and declare it to the Java compiler. So what are these primitive data types called? The 8 primitive data types are called byte, short, int, long, float, double, boolean, and char. Each data type is allocated a different number of slices or bytes in the memory. The most basic is a byte, which from its name is allocated just 1 byte. Short numbers are allocated 2 bytes. Int and float variables take 4 bytes, and that's why I reserved 4 bytes for the variable hours earlier in this video. Long and double numbers occupy 8 bytes. Boolean could vary depending on the virtual machine implementation, and the char data type takes 2 bytes. Notice that out of these 8 data types, 6 of them are numerical. And since they have different byte sizes, they can store different ranges of numbers, which we will explain shortly. It's also important to know that 4 out of these 6 numerical primitive data types are used to represent integers. The remaining 2 are used to represent floating point numbers, numbers with a decimal point. Before we explain each of these types in details, I have 2 questions for you. The first question is, what defines these ranges? For example, why does a byte represent numbers from -128 to 127? The second question is, why the positive range of every integer data type is exactly 1 less than the negative range? For example, a byte represents 128 negative numbers, but 127 positive numbers. The short data type represents 32,768 negative numbers, but only 32,767 positive numbers. To answer these two questions, let's start with a byte. It has 8 bits, and each bit can be 0 or 1. Since the binary number system is base 2, each column in your number adds a power of 2. 2 to the power 0 gives you 1, 2 to the power 1 gives you 2, and so on. So all zeros represent the number 0. All ones, if we add the columns, will represent 255. This means we have a total of 256 numbers to represent using a byte from 0 to 55 with all possible combinations in between. But all of these numbers are positive. What if we want to represent negative numbers? A possible solution is to think of the most significant bit, the bit to the most left, as a sign. 0 means positive and 1 means negative. If you look at this table, the first 128 numbers will have 0 in this bit. The second half of the table will have the most significant bit of 1. Since 1 means negative, we have 128 negative numbers to represent. In the positive range, however, we have to count for the number 0, and that's why we have the 0 and 127 positive numbers. Excellent. Now we know the different data types, how they are stored in the memory, and what range of numbers they can represent. Now, how do we use them? You use them by declaring variables. You choose the appropriate data type, followed by a variable identifier. Now you have reserved memory for the variable. To improve your code readability, you can actually declare multiple variables of the same type in a single line. So for example, if I have 3 variables, length, width, and area, and all of them are of type integers, then I can use int followed by 3 variable identifiers separated by commas, and of course terminate with a semicolon. Now let's explore each of the data types in detail by starting with the 4 integer data types. These data types can hold whole numbers only, and they can't hold numbers that have a decimal point in them. So for example, if you try to store numbers like 5, 10, negative 89, it will work, but trying to store a 5.5 in an integer variable will lead to a compile time error. If your code contains integer number written in the code, this number is referred to as an integer literal. In this example, the 100 is an integer literal. By default, Java will treat integer literals as int. Although the 100 in the example above is treated as an int since it's less than the 127, the upper limit of the byte, it can be assigned to a byte as well. If you try to assign an integer literal that is beyond the range of the data type, Java will complain. Byte and short data types do not perform operations in Java. If you add any combinations of these two data types, for example, a byte to a byte to a short, or short to a short, you will end up with an int data type. So for example, if you have a variable b of data type byte, and you perform an expression of b plus 1, the result will be int. This will be shown in a demo and will be explained in more detail in a future video. You have to be mindful of the ranges of each data type. Serious problems can occur if you are not. For example, we know that 127 is the maximum positive number you can store in a byte. Assigning 128 to a variable of type byte will not be accepted by Java, and it will give you a compile time error. However, we can still force Java to perform that assignment. This means that we can store 128 in the byte variable. This is called casting, and it will be explained in another video. Now, if you cast, what will happen is that it will lead to what is called a number wraparound. If you try to store a bigger number beyond the range of a data type, it will wrap around and start counting in the negative range. So for example, storing 128 in a byte is over the limit by 1. So this one will start counting from the negative range, leading to storing negative 28 instead. So if you are not mindful, you may end up subtracting instead of adding the 128. This is a logical error. Next, let's discuss the floating point data types. Floating point data types are the data types that allow fractions. You can use upper or lower case e to write the long floating point numbers. A number with fractions written in your code is a floating point literal. By default, Java treats floating point literals as double. Since Java is a strongly typed language, a variable with the type you declare must hold a matching data type. This means that if you try to store a floating point number in a float variable, Java will complain since the floating point literal is a double. Again, we can cast the double number in the float variable by adding the lower or upper case f after the number. The Boolean data type is a type that can take one of two values, either true or false. It can be handy for logic and conditions. For example, you can build a code that says if condition A is satisfied or if condition A is true, I will do X. The last primitive data type is char. Char data type can be used for a variable that will store a single character. Char literals are characters enclosed in single quotation marks. Remember, they could be escape sequences. For the computer to understand the characters, it has to convert it to numbers, zeros and ones. One way to represent the number is to use the ASCII code, which is the numerical code that maps the characters on a standard English keyboard. In this code, 1 byte is used to represent the characters. Out of the 1 byte, 7 bits are actually used, leading to 128 characters to be represented. Due to the need to represent other non-English characters from other languages, the 1 byte of the ASCII code became insufficient. And people extended it by adding one more byte, leading to what is called the Unicode. This is the system used to represent characters in Java. Each character takes 2 bytes, which means 16 bits. This is more than enough to represent every single character in all possible languages. To maintain compatibility with the ASCII code, the first 256 characters corresponding to the first byte represent the ASCII code. For example, if we want to store the letters of the word Java in the computer, this will be stored using a total of 8 bytes, 2 for each character. The uppercase J is represented using the 74, so this becomes 00 for the second byte and 74 for the first byte. Similarly, lowercase a will be represented as 0097. Lowercase v will be 118, and then again 00 and 97 for the last lowercase a. In this video, we will have the demo for the primitive data types. So I have a couple of examples here. The first demo is about assigning floating point number to an integer variable. We said this does not work. You cannot store a floating point number in an integer data type. So even if I put an int here, it will complain. It will say incompatible types, possible lossy conversion from double to int. So you cannot store floating point in an integer data type. Now, the other thing that we want to do is to assign the different types of the integer data types. So for example, I have an int which could take a -20. I have a long which can take a very long or large value of an integer. We could declare byte miles and then assign 120 to it. We could define a short minutes and assign 120 to it. That should work. So we can have examples like we have made a journey of certain number of miles. We took a certain number of minutes and our account balance is this, whatever checking is. And then it took us, or about days ago, Columbus stood at this point. So if I run this, it should give me all of these values and it runs smoothly, no problem. So let me comment this, and then let's check the byte. One thing that I would like to say is that 120 is less than what byte can store. We said 127 is the maximum or the upper bound. So if I try to store up to 127, it's not going to complain. However, once I start to say 128, which is beyond the range of a byte, now I get a compile time error saying incompatible types, possible lossy conversion from int to byte. Because above 127, we said an integer literal is treated as a type int, right? So if 128, by default, this is set to int, which doesn't match byte. All right. However, if it was less than 127 or equal to, that would still work. So the other demo here that we have is how byte and short have no operations. You cannot add or do mathematical operations using byte and short. So for example, here I could declare 120 I could declare minutes to be short and store 120 in it, which is fine. Now, what Java is going to complain about is that I try to add minutes to minutes, which will give me 240, which is fine. It's less than what short can store. But once I try to store this in short, it's going to complain. It will say that is a possible lossy conversion from int to short. And that's what we mean by byte and short have no operations. Adding short to short gives you int by default. All right, so this is going to be discussed further in a future video. Now, if I try to add 1 to it, right, and try to store it in a variable that is declared as an int, it's going to work. No complaints. All right, so this is something that you need to be aware of. Byte and short, they do not have any operations. All right, if you are doing, on the other hand, adding a long to an int, it's going to give you long. You can actually store that in the value d, right? Remember days, it was declared as long plus 1 is going to be added to days and then stored in long. It's going to work, no problem. All right, so that's for the long. The last thing about integers is going to be the wraparound. If you remember, we said if you force a byte to store more than 127, which is possible, it's called casting, and we will discuss it further in the future. This is how you do it. You are casting. You are telling Java, I know what I'm doing. Just put 128 inside X, which is of type byte. All right. So even if you do that, what will happen is that wraparound, right? So 128 is beyond the 127 by 1. So if you try to compile this and run it, you will get negative 128. Add one more. So you should expect what to see now. It's going to be negative 127 and so on. All right. So if you add like 5,000, it will go a couple of times over that range of 256 and it's going to give you negative 120. So you need to be very careful. Do not cast if it's going to create problems. All right, so the next is float and double. As we said, any floating point literal is going to be treated as double. So if you try and store that in a float, it's going to complain. All right, so it's not going to work because this is treated as double by Java. You are trying to store it in a float. Not gonna happen. All right. Also, we said that you could use the E to express long floating point numbers. So in this case, I could do something like this. Compile, run, and it's going to represent this by moving the decimal point to the right 4 steps. So 1 or 4 places, 1, 2, 3, 4, which is the 47,281.97. All right. What if you cast? We said floating point is double. You cannot store it in float. However, you could cast it, right? So something like this would cast this. It's going to work. It's not going to complain. All right. So I told Java, no, I know what I'm doing. Just put that. I know it's double, but I'm asking you to put it as a float in float s. So that is gonna work. Another way to cast is to use float like this. All right, which works with variables. All right. So if you have a variable k, for example here, because it was not declared, there we go. So if you have a variable, you cannot use an f at the end because that can confuse Java. Is it k or kf? So in this case, what you cast with is to use float between parentheses like this. The last two data types are the boolean. So boolean could be, as we said, it could take true or false. So if you say, for example, boolean tval to be true, and you print this, it's going to print true. All right. Here I'm saying not tval, like it's basically inverted. So in this case, it's going to say true or false. So that data type, it actually prints true and false as words. All right. It's not a string. It's just a data type. It's a unique data type called boolean, and it's going to be true or false. And this is actually boolean with b lowercase. The last one is the char. The char can take a character between single quotations like this. It will not accept a string. So if you use double quotes, it will complain. All right, and instead it has to be single quotation for this for the characters or the char data type. So if I do something like this, it's going to print the b uppercase. Now also, since it has to be a char, it has to be a single character, it will not accept a sequence of characters. All right, first of all, it's going to complain about this because you have two characters inside the single character quotations. It's not going to work. It will complain here. It says that's a string. All right, so unclosed character literal. That's not going to work. All right, so you have to convert this into a string instead. All right, the only thing that where it will accept two things is the escape sequences, because you remember we said that \n is not treated as two characters, even though they look like two characters, but that's something special treated by the compiler in a special way, and that's why it's escape character. It's considered the character. So I could embed something like this inside a string, and it's going to work. It's going to create that new line effect. All right, so that works. That's completely valid.